Imagine a factory where a car is built. The car goes through many workstations: frame, engine, paint, inspection. If only one car is in the factory at a time, the whole line sits idle while a station works. Pipelining is like letting many cars be in the factory at the same time, each at a different station. In a CPU and instruction, a tiny program step also has many stations: fetch, decode, compute, store result, etc. Modern processors need to be fast, but a single step instruction can take many nanoseconds. By splitting the work into stages and feeding a new instruction every clock tick, the processor can finish many instructions per unit time, just like the factory produces many cars per hour. Without pipelining, the clock would have to be slowed down to the longest step, wasting a lot of speed. Hence, pipelining is essential for the high performance we expect from today's phones, laptops, and servers. The classic 5-stage pipeline is the assembly line most textbooks use. The 5 stations are: IF instruction fetch. The CPU reads the next instruction from memory, like a worker taking the next car chassis from the warehouse. ID instruction decode and register read. The instruction is examined to find out what operation it is and which registers, tiny storage boxes, it needs, similar to a worker reading the blueprint. EX execute or effective address calculation. The arithmetic or address calculation is performed, like the worker attaching the engine. MEM memory access. If the instruction needs to read or write data from memory, for example load or store, this stage talks to the memory system, just as a worker goes to the paint booth. WB write back. The result of the instruction is written back to the destination register, like the final inspection station putting the finished car on the exit ramp. Each stage takes 1 clock cycle. While one instruction is in IF, the previous instruction is already in ID, the one before that in EX, and so on. After the pipeline is full 5 cycles, a new instruction finishes every cycle, giving a throughput of 1 instruction per clock tick. A simple picture. Cycle 1 IF instruction 1. Cycle 2 IF instruction 2 ID instruction 1. Cycle 3 IF instruction 3 ID instruction 2 EX instruction 1. Cycle 4 IF instruction 4 ID instruction 3 EX instruction 2 MEM instruction 1. Cycle 5 IF instruction 5 ID instruction 4 EX instruction 3 MEM instruction 2 WB instruction 1. Arithmetic operations, addition, multiplication, etc., can be heavy, so designers split them into several pipeline stages, just like a long road is divided into shorter segments with stops in between. Multi-stage ALU, an integer adder, can be broken into lower bits and higher bits stages. The first stage adds the low 16 bits, the second stage adds the high 16 bits plus any carry from the first. This allows each stage to be fast because it works on a smaller piece of data. Carry look-ahead adder CLA. A normal ripple carry adder would wait for the carry to travel through every bit, which is slow. CLA predicts the carry for each bit group in parallel using logic, like if the lower group will generate a carry, then the higher group receives it immediately. In a pipeline, the generate-propagate logic can be a stage by itself, and the final sum calculation another stage. Multiplier pipeline. Multiplying two 32-bit numbers can be done with a sequence of partial product additions. A simple hardware multiplier may use an array of adders that work over several clock cycles. Each cycle adds a new row of partial products. By pipelining, each row addition becomes its own stage, so a new multiplication can start each cycle while earlier ones are still being summed. These pipelines make the big math operation seem like a series of small, quick steps, keeping the overall clock fast while still delivering the correct final result after a few cycles. Mathematical view. If a full-width adder takes t sub add seconds, splitting it into k equal stages gives each stage a latency t sub stage equals t sub add divided by k. The clock period can now be set to t sub stage, allowing a higher frequency. When many instructions share the same pipeline, 3 kinds of problems called hazards can appear. Data hazard. One instruction needs a value that a previous instruction has not yet produced. Example: add R1, R2, R3 writes R1, and the next instruction sub R4, R1, R5 reads R1 too early. Forwarding bypassing. Directly send the result from the X or MEM stage, to the ID stage of the next instruction, skipping the register write read. Stalling, insert a bubble, a do-nothing cycle so the second instruction waits until the value is ready. Control hazard, the pipeline does not know which instruction comes next because of a branch. For example, if R1 equals 0, go to L until the branch decision is resolved, usually in X. The next fetch may be wrong. Branch prediction, guess the direction. If wrong, flush the wrongly fetched instructions, throw away the bubbles. Delay slots, compiler places useful instructions right after the branch that will execute regardless of the branch outcome. Structural hazard, two instructions want the same hardware resource at the same time. For example, two instructions need the memory unit in the same cycle. Solution, design the pipeline so each stage has its own dedicated hardware, or insert stalls when sharing is unavoidable. A child-friendly analogy. Imagine a kitchen where a Chef X stage needs a whisk resource. If two recipes both need the whisk at the same moment, one chef must wait stall, or the kitchen must have two whisks duplicate resource to avoid a clash. Throughput, how many instructions finish per unit time, usually instructions per clock cycle. IPC, after the pipeline is full, ideal throughput equals 1 IPC. Latency, how many cycles an individual instruction needs from start to finish. In a 5-stage pipeline, latency equals 5 cycles. CPI, cycles per instruction, average cycles required for each instruction. For a perfect pipeline with no stalls, CPI is approximately 1. If stalls occur, CPI equals 1 plus stalls per instruction. Example calculation. Suppose a program has 1,000 instructions. On a 5-stage pipeline, the clock frequency is 2 GHz, period equals 0.5 nanoseconds. Assume on average each instruction causes 0.2 stall cycles due to hazards. Then, CPI equals 1 plus 0.2 equals 1.2 cycles per instruction. Total cycles equals 1,000 times 1.2 equals 1,200 cycles. Execution time equals 1,200 cycles times 0.5 nanoseconds equals 600 nanoseconds. If we had a non-pipeline processor that took 5 cycles for every instruction, no overlap, the time would be total cycles equals 1,000 times 5 equals 5,000 cycles. Execution time equals 5,000 cycles times 0.5 nanoseconds equals 2,500 nanoseconds. Thus, pipelining gave a speed up of 2,500 nanoseconds divided by 600 nanoseconds, approximately 4.2 times despite the stalls. Throughput can also be expressed as IPC equals 1 divided by CPI, so here IPC equals 0.83. Explanation. A pipeline works best when each stage takes about the same amount of time, otherwise the longest stage forces the whole clock to be slow, the bottleneck. Assume we have a 4-stage pipeline that needs to process a total of 40 nanoseconds of work, the sum of all stage latencies. Let the latencies be T sub 1, T sub 2, T sub 3, T sub 4 with T sub 1 plus T sub 2 plus T sub 3 plus T sub 4 equals 40 nanoseconds. We want to minimize the clock period T equals the maximum of Ti. The optimal solution is to make all Ti equal. Ti equals 40 nanoseconds divided by 4 equals 10 nanoseconds. Thus the clock can run at 1 over T equals 100 megahertz. If we accidentally make the stages uneven, for example T sub 1 equals 6 nanoseconds, T sub 2 equals 8 nanoseconds, T sub 3 equals 12 nanoseconds, T sub 4 equals 14 nanoseconds, the clock period becomes T equals 14 nanoseconds, limiting frequency to 71.4 megahertz, a 28% loss. Mathematical optimization. For a given total work W and a desired number of stages K, the minimum possible clock period is T min equals W divided by K when all stages are perfectly balanced. In practice, designers add a small margin epsilon for wiring delays, so T equals W divided by K plus epsilon. This balancing act is similar to cutting a log into equal pieces. The longest piece determines how fast you can carry them one after another. Superscalar processors are like a kitchen with multiple identical assembly lines. Instead of feeding 1 instruction per cycle, the CPU can feed n instructions per cycle, where n is the issue width. Multiple issue. In a two-issue superscalar, each clock tick the instruction decoder can send two independent instructions to two parallel pipelines, often called lanes. If both lanes are busy and the instructions do not depend on each other, the processor can finish two instructions in the time it would have taken one. Throughput gain example. Assume each lane is a 5-stage pipeline with a 1 GHz clock, 1 nanosecond period, and no stalls. A scalar processor one issue completes one instruction per nanosecond, which is 1 giga instructions per second. A two-issue superscalar can complete up to 2 instructions per nanosecond, which is 2 giga instructions per second, a theoretical 2 times speed up. Real hardware often sees less gain because of hazards and limited independent instructions. If on average only 1.4 of the two slots are useful, CPI becomes 1 divided by 1.4, approximately 0.71, still better than 1 but not double. Superscalar designs also add dynamic dispatch logic, reservation stations, scoreboard, to decide which instructions can go to which lane, similar to a traffic controller directing cars to the fastest open lane. Out-of-order execution lets the processor reorder instructions internally to keep the pipelines busy, while preserving the program order when results become visible. Key structures reorder buffer, a queue that records the original program order of all in-flight instructions. When an instruction finishes, its result is placed in the reorder buffer, but it is not committed, written to the architectural register file until all earlier instructions in the buffer have also finished. This ensures correct visible order. Reservation stations. Each execution unit has a set of stations that hold instructions waiting for their operands. When the needed operand becomes available, either from the register file or from a previous instruction's result broadcast on the common data bus, the instruction can fire even if earlier instructions are still stalled. Illustrative scenario. Instruction A, load R1 from 0 offset of R2, loads a value from memory slow. Instruction B, add R3, R4, R5, simple add fast. Instruction C, multiply R6, R1, R7 needs the result of A. In a scalar pipeline, B would wait for A to finish, causing a bubble. In out of order, A is dispatched to the load unit and occupies a reorder buffer entry. B's operands are ready, so B is sent to an ALU reservation station, executes immediately, and writes its result to the reorder buffer. C cannot execute until A's load finishes, so it stays in the reservation station. When it finally completes, its result is broadcast. C sees the value, executes, and finally the reorder buffer commits the results in order A, B, C. Thus the CPU keeps the fast unit busy rather than stalling, raising overall throughput. Explanation. Real chips show how the ideas above are turned into practical designs. MIPS Classic Textbook. MIPS processors use a clean 5-stage pipeline with fixed length stages and simple forwarding. They demonstrate the basic concepts without many extra tricks. A RM Cortex-A series uses a deeper pipeline, often 8 to 12 stages, and includes branch prediction, out-of-order core Cortex-A 75/A76 with ROB and multiple issue. The RM designers balance power and performance, so the pipeline stages are not all equal. The fetch stage may be faster than the memory stage. RISC-V open source cores like Rocket or Boom show both scalar and superscalar variants. Rocket is a 5-stage in-order core, similar to MIPS, while Boom is a 4-issue out-of-order design that implements ROB, reservation stations, and aggressive speculation. Trade-offs observed. Power versus speed. More stages and more parallel units increase clock frequency, but also increase switching activity, leading to higher power consumption. Mobile chips, for example a RM Cortex-A55, use shorter pipelines to save energy. Complexity. Adding out-of-order logic, branch predictors, and multiple issue units makes verification harder and silicon area larger. Simpler cores, MIPS and Rocket, are easier to design and are used where low cost is critical. Clock frequency limits. Deep pipelines can run at greater than 3 GHz on desktop CPUs, but the latency of a single instruction also grows more stages. This is fine for workloads with many independent instructions, media decoding, scientific code, but hurts latency-sensitive tasks. Instruction set impact. RISC-V's modular ISA allows a designer to include or omit features like atomic instructions, which may require extra pipeline stages. ARM's Thumb2 mixed-length instructions add a variable-length decode stage. Overall, the theory of pipelining translates into real design decisions. How many stages, whether to duplicate resources, how much speculation to allow, and where to spend the silicon budget.